Hi everyone. So I know that we didn't have a chance to go over this homework assignment in class, so I figured I would just do it with you online. So pretend we're in class right now. So in this problem, you are sketching a graph of stopping voltage versus frequency for two different metals, one with a high frequency and one with a low one. So I won't put numbers on it, but we'll label both axes. So you got to figure out what the axes are. Kind of gave that away though. This one's stopping voltage, which we can call Vs. It's the y-axis. Gives you the kinetic energy, or what's like the kinetic energy anyway. There it is. The other axis is going to be the frequency, so we put frequency over here. There we are. Now both of the lines will be straight lines. It's just the one with the low stopping voltage, with a low threshold frequency, should be here. That one has a low threshold frequency because you can see that the frequency value is lower. That is to say it's closer to zero. There's the one with the high threshold frequency. For both of them, it doesn't take any voltage to stop the current from flowing at the threshold frequency. And then as you increase the frequency, as you make the light more orangish or bluish or purplish, then you do need to apply an increasingly high stopping voltage to actually stop it. The slope should be the same because of the relationship E equals HF. Since stopping voltage is related to kinetic energy, and H is a constant, these need to be straight lines with the exact same slope. So again, the one on the left is the one that has the low threshold frequency, easier to knock off electrons. And the one on the right is the one that has the higher threshold frequency, more difficult to knock off electrons. Okay, so number two, we've got a particular metal that requires a light of wavelength 600 nanometers, which is in the reddish-orangish range, to cause an electron to be ejected. So that's 600 nanometers is 600 times 10 to the negative 9, which is 6 times 10 to the negative 7 meters. So now you're trying to find the threshold frequency knowing the wavelength. So for that one, we just use the relationship that C equals lambda F. So 3 times 10 to the 8th is equal to lambda, which was 6 times 10 to the negative 7 times the frequency. So that gives us that the frequency is going to be equal to 3 times 10 to the 8th divided by 6 times 10 to the negative 7th. That is negative 7. And that should be 5 times 10 to the 14th, and that's hertz. Okay, so the next step I've asked, using the answer for part A, which gives you the frequency and the equation equals HF, what's the minimum energy required to knock an electron off that metal? So that's E, that's going to be the energy, is equal to 6.63, 3 times 10 to the negative 34th. That's going to be times our 5 times 10 to the 14th. Well, it's going to be something times 10 to the negative 20th. Looks like 33.15 times 10 to the negative 20th, which is 3.3 times 10 to the negative 19th, and that's joules. Okay, so the next problem says, what's the energy carried by a photon with a wavelength of 500 nanometers? Well, so for here, you're going to do the same kind of situation. You still need to find the frequency using that the speed is equal to wavelength times frequency, but instead of doing C is equal to 3 times 10 to the 8th divided by 6 times 10 to the negative 7, it's now going to be 5 times 10 to the negative 7, which gives us now 6 times 10 to the 14th. And then when we want to figure out that energy, we're going to take HF again. So the energy, sorry, this is a lowercase c. So the energy is HF, which is 6.63 times 10 to the negative 34. And that's times 6 times 10 to the 14th. And we'll use the calculator, I think, probably to figure this one out. Can't quite do that one in my head. 6.63 times 6. The decimal points should be the same, so we get 3.978, or we can call that 4.0 times 10 to the negative 19th. And again, that's in joules. All right, now, when we want to use the answers for part C and D in the equation HF equals HF0 plus kinetic energy, we can find the kinetic energy of the electron that's knocked off, because we know that the 500 nanometer wavelength photon has an energy of 4.0 times 10 to the negative 19th, and that equals the threshold energy, which is 3.3 times 10 to the negative 19th, and then that's plus the kinetic energy. So the kinetic energy becomes, this is of the maximum kinetic energy of the electrons that are knocked off. So the maximum energy they can possibly have, 0.7 times 10 to the 19th joules. All right, well, fair enough. Then it says determine using the information of kinetic energy and the mass of the electron, determine the speed of this electron. So here we're going to go back into Microsoft Equation. And we know that kinetic energy, I'll just call this a K in this case. So the kinetic energy K is equal to 1/2 mv squared. And we want to find out how fast the electron is. Now we should be able to manipulate this equation and make V the subject of it. It should be the square root of 2K over m. We'll do it this way. 2K over m, which gives us the square root of 2 times 0.7, which is 1.4, times 10 to the negative 19th. I think that's right. Yeah, it is not. It is right. This should be negative 19th here. Sorry, the window's open. I'm not playing Lady Gaga. Sorry, it's done now. All right, so we can use our calculator. We take 1.4 times 10 to the negative 19th divided by 9.11 times 10 to the 31st. Big number, take the square root of that, and that gives us, well, a slightly smaller number, 3.9 times 10 to the 5th, which is pretty fast, but not relativistic by any means. So Einstein wouldn't be very mad. That's meters per second. That's the speed that an electron is knocked off. And we could figure out the voltage required to stop it if we needed to. Okay, so number 3 says, explain wave-particle duality in your own words and give an example of something a wave does but a particle doesn't. Now here you should say diffraction or interference. Electron diffraction is the example. Wave-particle duality, of course, it means that at a very, very small scale, particles act like waves and waves act like particles. And photons and electrons are the only two things that I know of that do that. Something that a particle does that a wave doesn't is it has collisions. To knock off other particles instantly. You could put this in other ways, but if a wave is going to knock off a particle, it's going to do it by vibrating it more and more and more until it finally gains enough energy to leave. But if a particle is knocking off another particle, it just does that instantaneous transfer of momentum, and so that's the photoelectric effect there. Okay, so here I've asked for the de Broglie wavelength for a couple of things. One is an electron and another is a car, and this is always a good one to look at. The equation for the de Broglie wavelength is, just a second, I'll put it up here. The equation for the de Broglie wavelength is lambda, which is the wavelength, is equal to h over mv. So if it's an electron moving at 6.6 times 10 to the 6th, which we've seen is a reasonable speed, that's going to be 6.63 times 10 to the negative 34. It's Planck's constant divided by 9.11 times 10 to the negative 31. That's the mass times the velocity, which is 6 times 10 to the 6. So we'll figure out what that is. 6.63 times 10 to the 34. That's negative. Divided by 9.11 times 10 to the negative 31. There we are. And then divided by 6 times 10 to the 6th equals. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's about 1 times 10 to the negative 10. 1e negative 10 meters, which we could call that 0.1 nanometers. And that's in the X-ray range. So if it exhibits X-ray diffraction or interference, then you would see it for something with a wavelength like that. It's a small wavelength, but not super small. On the other hand, if we do the same thing with this car, we have just the exact same equation. We have the wavelength is h over mv, which is 6.63 times 10 to the negative 34 divided by, and then it's 1,000 times 20, so you can say it's 20,000. That's right. Yeah, a 2 with 4 zeros, that's right. So that gives us 3.3. That's 10 to the negative 38. That's a tiny, tiny, tiny wavelength, so nothing exhibits wave properties like that. So it's got to be the electron. That's because nothing is small enough to diffract, well, to cause diffraction with a wavelength like 10 to the negative 38. I mean, that's just tiny. So if we look back over these problems again to make sure we got it right, there's the photoelectric effect with the electron that's hard to get off and the electron that's easy to get off. There's the calculation of the kinetic energy of the electron. Ends up at 3.9 times 10 to the 5th, seems reasonable. Particle wave duality and the de Broglie wavelength. So I'm off to play Monopoly with my son. This is Alex. He's going to say hi to you right now. Alex, say hi.
Hi.
Okay, everybody, that was Alex. I'm off to play Monopoly. Have a good day.